So they roll the marble off the table. So it leaves the tabletop. I think you all believe, and probably rightly so, that the marble will eventually hit the floor. What if I wanted to place a cup on the floor somewhere where I could catch the marble? Tell me, what are some things that would determine where the marble strikes the floor? Things that you could control when you release the marble. Yes, sir?
Initial velocity.
All right, so I could roll the marble faster. If I roll it too fast, would you all agree? It'll probably strike the floor over here. But if I roll it too slow, it'll strike the floor over there. So I think initial velocity does play a role here. What's something else I could control here? Yes, sir?
The distance from the edge of the table?
Well, I think that's where the cup goes, right?
No, the distance of the marble.
I could. This is true. But I think that would more be about how fast the marble leaves my hand. If I give myself more distance, it just gives me a bigger distance to push over. But once it leaves the table, I can't push on it anymore. So I'm going to say that this distance probably plays less of a role than you think. Something else? Yes, sir?
Distance from the table to the ground.
Would you agree that a shorter table would mean that the marble has less time in the air? A taller table would have more time in the air. So yeah, I think that probably how high the tabletop is would probably have something to do with this. Can you think of anything else? Yes, sir?
I was going to say maybe like friction on the top of the tabletop.
It would, but we're really focused on what happens after it leaves the tabletop. So I'm trying to ignore those factors. I think there's one more thing that our prior knowledge discussion should have kind of steered you towards. Yes, sir?
The distance of the cup from the table.
Well, we're trying to hit the cup, so let's say that's a fixed distance. Yes, sir?
Would the weight of the marble be a factor?
Interesting. 2 classes have brought up the weight of the marble. When we use those motion equations, did we ever have to worry about the weight of the object we threw? No, that's a curious solution too. I'm sorry, a curious idea. There's probably a reason for that. So that will be coming, but actually that plays a much less role than you might imagine. And since I don't want to spend the entire class period trying to get this from you, I'll allow one more person maybe to demonstrate some insight of something else. And I'm really trying to bring out the kid in you guys, because anybody who's ever played with Hot Wheel cars probably knows what I'm thinking about next. Yes, sir?
The angle.
The angle. I would have thought a golf pro would have come up with that. But oh well. Yeah, I mean, I would argue that if I launch it at an angle, that might have something to do with where it lands. I'm not sure of all the implications of the angle, though. The bigger the angle, the longer it's in the air. But we just found out from Trig that as you change the angle, you kind of manipulate how fast it might be moving sideways. Wouldn't you all agree? I mean, it's possible if you launch it at 90 degrees, it doesn't move sideways at all. It's true? So, launch angle, which I'll use a lowercase theta for. Based on your performance just a little bit ago on our practice, I can't assume too much. So give me just a moment of I'm just begging your attention on this one. Think back to elementary school for just a minute. You guys remember this kind of paper? So when we think about what theta looks like, if an S, lowercase s is down there, and say an uppercase B looks like that, the way I draw theta, this is supposed to be a lowercase theta, but lowercase theta still fills up the entire staff. It doesn't go quite to the top, just like lowercase letters, except for the L, don't go quite to the top. But it's different from a capital theta. Capital theta, when it's drawn, is drawn as a complete, a complete circle with like an I in the middle of it. So this is considered a lowercase theta, and it's how I will always draw it. It would make sense when you write your theta that it would be taller than perhaps the trig function that comes before it. Does everybody follow? I just want you guys to know what these letters look like. It's not like you had a class in Greek letters. And so I'll tend to try and stop so that we all have an agreement as to what we call theta. We generally use theta to indicate angles in physics. However, there will be times when we have more than one angle. If we do, we will probably use another Greek letter, phi, for that angle. So I generally use theta, sometimes we'll use phi. Okay? They're both Greek letters. Phi and theta are drawn about the same. Launch velocity is a little different in that it could be a velocity in both the x and the y direction at the same time. As we said, it could be launched at an angle, so we will use a v with a small circle for that, v naught, as the launch velocity. And last, we have the height. The height to which it's launched or the height to which it lands. This is also known as the vertical displacement. And your book uses a delta y for vertical displacement. Okay. So, to put all this together, I want to give a definition of what projectile motion is. A projectile is an object that moves in 2 dimensions, but only experiences an acceleration in 1. I'll say that again. For us, because we're looking at kind of a simplified version of projectiles. But for us, a projectile is an object that moves in 2 dimensions, but only experiences an acceleration in 1 of those dimensions. When you launch an object, we know that it tends to have a curved path through the air. A projectile is being accelerated in 1 of these 2 dimensions. It's being accelerated by gravity, which acts in 1 of the 2 dimensions. I will refer to the 2 dimensions as the horizontal dimension and the vertical dimension. Now, just a quick aside here. I've got baseball players in the room and golfers in the room. Projectiles seldom move in 2 dimensions. In the real world, projectiles move in 3 dimensions. If it's a golf ball, the dimples on the golf ball grab hold of the air and the spin of that golf ball causes it to move in 3 dimensions. You might aim straight in front of you, but if you hook or slice, you know it's because of the way you hit the ball caused it to spin, unfortunately for you, in perhaps an undesirable direction. It grabbed the air and created a second acceleration that pushed the ball to the side. If you're watching the pitcher throw the ball, you know that they are very aware that the grips of the ball, the threads, can grab hold of the air and cause the ball's path to change as it's pitched. Thus, a curveball and a slider can try and cause the batter to believe the ball is going to be in one place, but the curvature of its path can be unpredictable and try and get them to swing anyways. These are 3-dimensional motion. We're going to kind of ignore that extra part for a little while because that stuff can be complicated. So for the time being, we're going to assume that the air isn't pushing the object around. I think this will be complicated enough for most of you. Fair enough? All right. So we launched the object. The moment it's launched, it has 2 velocities. It has a velocity in the y direction and a velocity in the x direction. It's important to note that the object is going to appear at many places during its motion. But, and this might be the most important thing I say, it experiences an acceleration in only 1 dimension, which means that the horizontal dimension is unaffected by that acceleration. That means that the horizontal velocity of the object is a constant. It will stay the same. Now, folks, make that big and bold. It doesn't accelerate. So whatever the horizontal velocity is when it's launched, that will be the horizontal velocity when it lands. On the other hand, the vertical velocity will be acted on by gravity, and therefore it can come up to a stop at its maximum height and then begin to create a velocity that's downwards. The y velocity is constantly changing. It'll be launched with an initial y velocity, but the moment it gets into the air, gravity will take hold of it and change that y velocity. What's important to understand is that this object will have motion in 2 dimensions. It's going to have a horizontal velocity and a vertical velocity. Wait, one more sentence. It is the time of travel that is the same for both. It is the time of travel that is the same for both. It travels the same time going up and down as it does going sideways. That's what we'll be working towards.